So, thanks so much for the possibility from the International Committee and the organizers for giving this opportunity for us to, or for me to present some of the work that we're doing in Trondheim at the moment. I'd also like to draw the attention towards my co-authors, because this has been a cooperation between NTNU, SINTEF, and Hydro. Let's see if it works. Okay, yes. So this will be the outline of the talk today. I'm going to give a very short introduction about the lean aluminium magnesium silicon alloys that we've been looking at, and then tell you a very short what our project goal was, then move on to lithium and germanium additions and tell you about the results we got about that, hardness, precipitation, and give you some atomistic details of the cross sections that we got, and finally some density functional theory. So in this work we're looking at 6,000 alloys for extrusion, and it's going to be lean alloys, so as little solute additions as possible. And then we're mainly going to focus in this talk for the TM, transmission electron microscopy, on the precipitation of these hardening phases. So just for those of you who may be forgotten about this, these needles, they go along the 3001 aluminium directions, and we start out with this supersaturated solid solution, and as we do aging treatment, we get atomic clustering, GP zones, and beta double prime, which we associate with peak hardness of the alloy, which is going to be the main features here. So in this project, we would like to have a minimal amount of solute added, because we want the extrudability to be better or as good as possible. But we also want to increase the material strength of these lean alloys. And then further also we want to characterize the precipitate phases. So we all know we have aluminium, of course. We also have magnesium and silicon in this 6,000 system. And based on actually quite a lot of work, we have chosen 4 alloys because lithium and germanium gave some really good results separately in these alloys, and we would like to do a combination of these to see if that also further improves the macroscopic properties. So these are the 4 alloys we have, both in weight percent and atomic percent. We have 1 reference, very lean, 1 lithium added alloy, and 1 germanium added alloy, and then 1 alloy with lithium and germanium. So just want to point out that it's very little additions here, just 0.01 atomic percent of germanium and 0.04 atomic percent of lithium. And you might maybe want to notice that it's actually about the same amount of effective solute for precipitation in the different alloys. Very briefly, we are heat treating at 195 degrees Celsius, and you might maybe want to notice that 0 hours is now where we have reached this temperature, but it's actually then already aged for a little while. Yes, so the hardness measurements we got were, as expected, maybe the reference alloy quite low in hardness. Then by adding some lithium, we see a clear increase, and further adding germanium, we get even better hardness values, and you can start to see that peak hardness occurs after a shorter aging times. And then finally adding both lithium and germanium gives us the best result here, and you're actually almost at peak hardness when you have reached your goal temperature of 195 degrees Celsius. So we'd like to have a look at the 4-hour aging condition in TEM, and it looks like this. Very quickly got the results here. So we have the reference in the upper left here, and you can see that the precipitate needles going in the 3 directions here, they are relatively large. Adding lithium, they decrease in size, and you get a higher number density. And then further on with germanium, the same happens, and we get the smallest needles actually with the highest number density for this lithium germanium added alloy. If you're not convinced, this is a table with a number density based on quite a lot of statistics from TEM. So you see the reference here, it's almost gone relative to the others. It's 170 precipitates per cubic micrometer. And then actually by adding lithium and germanium, we end up with 23,000 precipitates, which is quite a bit. And again, these two alloys have exactly the same amount of effective solute for precipitation. So then you can see how you can change you can do a significant change in the precipitation by adding different elements to the alloy. Maybe have some time for this slide. We also did more statistics. You can see that the needle lengths are decreasing steadily from the reference towards the aluminium alloy with lithium and germanium. And then also the same happens with the cross sections, needle lengths. Number density is increasing steadily, and we actually get about 31 HV hardness difference between the alloys. But we're not only interested in looking at how many precipitates we have, although they correspond really nicely with the hardness increase. We also want to see how these added elements are affecting the precipitates. Are they actually entering the precipitate structures? So here are some high-angle annular dark field scanning TEM images. These are also called maybe set contrast imaging. So you can get atomic number contrast, brighter columns, heavier elements. So this is the reference alloy. You can see a quite large beta double prime as expected. By adding lithium, some other things start to happen. You get dark areas, suggesting quite a bit of lithium. And you also get some stacking variations of the beta double prime molecules. By adding germanium, you start to see quite a lot of bright columns, making up a hexagonal network. And also, in the same cross-sections, you have beta double prime still. And then, finally, lithium and germanium gives us some of the same features, actually. However, problem is, where is lithium? So we need to check that. This not just enough to say that it's dark in this area in the middle. We also want to know if there's lithium in the beta double prime part. So unfortunately, EDS and EELs are not really suitable because you get almost 100% probability of a shear electron emission with EDS, and magnesium and lithium energy loss edges would actually overlap in EELs. So what we want to do is to use the SmartLine software, image registration code by Louis Jones, that optimizes the signal-to-noise ratio and creates a stack of stacks up the images of about, we used 40 images in this case. So what we get then, it's a very different image. You get some really dark columns that are very systematic in beta double prime, which should then correspond to lithium because it would give really low intensity in this imaging technique. So then we can give a model of this beta double prime I in the lithium containing alloy. Now we also wanted to check this by density functional theory calculations. So this has actually been done by Inga Ringdalen and Jesper Friis, who's here at ICA. So I realize this is a lot of information in one slide, but I can give you the quick version here of the results. We have the formation enthalpy per atom as a function of the percentage of magnesium that has been substituted by lithium. And then we get the most favorable configurations now for magnesium at the central position and aluminium at the central position. We both get the most favorable configuration is actually lithium at these Mg3 sites, which is exactly what we saw from the experimental results. Also, it's slightly more favorable for magnesium to be at the central position for these lithium-containing molecules. Okay, summing up the behavior of lithium, we see that the lithium prefers magnesium sites in beta double prime. There also seems to be a higher probability of this beta double prime stacking variation, which I'll come back to shortly. And we also see that it's actually particular sites, magnesium 3 sites, that are occupied first by lithium. Okay, germanium alloy. Then we get slightly different features. We have this really bright column area and some beta double prime areas. So some more examples. This hexagonal network, it's actually quite common, appears in almost all the cross sections with germanium. So it's a hexagonal network of germanium columns. But we also get these stacking variations of the beta double prime ice or molecules. And in addition, we see that germanium seems to like the Si2 sites in beta double prime. So these are the stacking variations that I've been mentioning. We see that we have 3 different types that seem to appear. And it's the normal one, beta double prime. But you also have the second type, beta 2 double prime, and then beta 3 double prime. They all have the same space groups, but you see that they actually configure quite differently. And what's maybe the most important thing to notice here is this X. These are vacant columns that appear in this beta 2 configurations here between aluminium columns. So you can actually get less solute to create the same area of the precipitate, so to speak. So you can save some solute to get the same precipitation in these alloys, in theory. Okay, so then we have the behavior of germanium. Try to sum that up. It seems to create a hexagonal germanium network, like in these columns here. But we also have occupation in the silicon columns in beta double prime. And thirdly, we also get a much higher probability for stacking variations in these beta double prime ice. And I'm not just saying it's a higher probability, but we have also done some DFT calculations on this, and it's favorable for germanium, according to the DFT calculations, to occupy silicon sites in the beta double prime also. Okay, so then the final alloy with lithium and germanium. It's a little bit more tricky because we don't see this very clear systematic dark colors at magnesium sites for beta double prime, like here. You can see both of these sites are actually darker, so we don't get the same systematic magnesium 3 sites occupation by lithium, apparently. We do also see a higher intensity at the silicon sites, so there seems to be germanium at some extent. So we've added this is the unit cell of a normal beta double prime with the suggestion of the molecule for this alloy. So we've added this diamond element, D, because both silicon and germanium are diamond elements. We're not quite certain how much germanium is occupying each column, so it seems to be some intermixing of the two. Also because there is no really clear low intensity at these magnesium sites in the beta double prime molecule, it seems that lithium would be favorable to go to all of these, depending on where in the eye it is. So then, based on all of this information, these are the models of the beta double prime ice or molecules, if you want, in our 4 alloys. The reference alloy with only magnesium and silicon should look a bit like this, we believe. Quite generally accepted in literature. And by adding lithium, we then get lithium occupying these 2 sites. Otherwise the same, and also magnesium at the center, because that seemed much more favorable from DFT calculations. Thirdly, we have the germanium added alloy with a diamond element here at the silicon positions, partly occupied by germanium. And finally, lithium and germanium added alloy, we get lithium and magnesium probably at all these sites, and some mixture of germanium and silicon at the silicon sites. Yes. Okay, so summarizing. We see that when we replaced some of this magnesium and silicon with lithium and germanium, there's this significant increase in material strength, and there's a huge increase in the precipitation of the hardening phases. We also see that actually the combination of lithium and germanium gives us the best or highest strength. It's quite a significant increase compared to the reference. And we also see that germanium seems to occupy silicon sites, lithium occupies magnesium sites in beta double prime, and it's most favorable in the lithium-containing alloy for lithium to occupy Mg3 sites. Both elements seem to cause this higher frequency of stacking variations of the molecules. And finally, we're proposing this model of the beta double prime molecule for the alloy with both these exotic element additions. So I'd like to finally acknowledge the funding for this work. It's quite a lot of different partners. And yeah, I guess that's the talk. Thank you so much.